and distributed systems guys and database folks, all of whom have some shared interest in trying to reason about data at scale. So from a programming language perspective, we think about the notion of what data means, how it's generated, how it's consumed, how do we reclaim it, what computation means when you have lots of data and they don't happen to all reside in the same place. Systems folks have an obvious interest in building systems that can tolerate large amounts of data without losing efficiency. And databases are, the name of the game in databases is data. So yet, if you look at the way that the field has evolved, you'll find that until very recently, what people have typically done is politely listen to what the other says and then promptly ignore it and go ahead and do their own thing anyway, right? So even though there may be ideas from the PL community that may have beneficial impact on the way we write databases, we design databases, or we build distributed systems, it's very rare to find instances where that's actually been transplanted into practice. And the same issue arises from the other side as well. But something very interesting happened a few years ago, and that was the widespread emergence of cloud services and big data and machine learning and all these things that required lots and lots of cycles that simply could not reside on a single device. And then all of a sudden, the problems became really, really hard for any one community to actually tackle on their own. And so that led to some interesting design choices. And what I'll spend today talking about is what those design choices are and how we can think about it as programming language researchers and implementers. So, right, the world is filled with clients and services that clients use to sort of store stuff, retrieve data, manipulate data in various ways. And so it's all very pervasive. But if you look at the sort of architecture that all of these services adhere to, they broadly fall into a common theme. There's a client. The client talks to a browser, to some kind of interface that allows him to access the service in some form. There's some server that sits around that responds to these requests. The server may have caching. It may do all sorts of fancy things to improve efficiency. But at the end of the day, all of that work feeds into some storage system, right? And the storage system is where a lot of the intelligence in this architecture resides. In particular, it means that we can afford to have all of the upper layers in the system be completely stateless. So if my browser disappears, if the server goes down, it doesn't mean that my bank account vanishes from the planet. Bank account is still sitting there. I just can't access it. But there's some expectation that the data that I wrote, the deposit that I made, the withdrawal that I did has been recorded somehow, right? Even if all the intermediate layers have disappeared. So the question that we want to ask is, what should we do about architecting that little box? Now, as long as that's just a single box, it's pretty simple, right? It's a server that sits in my room. I can manage it fairly easily. And we know over 40 years or 50 years of computing how to design such things. The challenge is what happens when that server is in fact not a single device, but a multitude of devices that may not necessarily even reside in one physical location, that may be transplanted across the globe. Now all of a sudden things become a little bit more challenging. So the question is, what do we have to offer in thinking about designing systems that have those kinds of features? So if you think of the way systems have evolved, in the beginning, we had systems which had a very simple interface between the computational units that they manipulated and the storage itself, right? There was a little bus, a little channel through which computation gets run on one side and it accesses storage and data on the other, right? And in this universe, in this scheme, there's a very strong relationship between computation and memory. In other words, when I write a particular location to memory, I expect that if I do a subsequent read, I'm going to read that value, right? There is a very, very tight interconnection between computation and data, right? After a point, people discovered that that bottleneck between storage and memory was expensive. There was energy cost. There was all sorts of other architectural issues that throttled, that provided tight bounds on how much performance we could gain. So people said, well, let's use parallelism. Let's bring multiple cores into the picture. And we'll allow these cores to have their own local caches. And these caches will eventually interface to some common memory. Once that happened, things became a little bit more complicated. Now, there's no single source of data. There's, in fact, data, the same data entity can reside in multiple places within this sort of pipeline. And we run into this question of thinking about what it means when I have a particular piece of data. When I refer to a particular variable, do I refer to the variable that's sitting on my cache, that's sitting in my write buffer, that happens to be sitting in memory? And what happens if there's two threads or two processes running on different cores that are doing that? And this leads to this large, complicated morass that we commonly refer to as memory models, right? But even despite that level of complexity, we find that there is still some rationale. It's not as though I can sort of read values from thin air. The value has to sit somewhere, and the only choice is which of the particular places it might reside in this memory hierarchy am I going to read this value from. And there is some sense that when I do a write, it's not the case that this write is going to have no relationship with other writes that have been applied to the same location. In other words, if one process writes x and another process, one process writes x with the value 1 and another process writes x with the value 2, I'm either going to see 1 or I'm going to see 2 in memory. It's not like I'm going to ever see 3. Right? So there is some guarantees that we can apply that gives us some hope that we can reason about these kinds of systems. The problem is that once we break the notion that there exists a single architectural framework in which we can go from computation to memory, for example, as we see in the bottom picture, where it's just a bunch of servers sitting across the globe, writing data and then reading what other people have written in arbitrary ways, that we run into that we no longer have the comfort of thinking about things in the sort of rational way that we could for the first two pictures. In other words, when I write a piece of data in the third picture on some server sitting in North America, what guarantees do I have that someone in Asia is ever going to see it? And if they do see it, how do I know that they're seeing the thing that I wrote, that they're not seeing something else that somebody else wrote that I have no knowledge about? And once we open up the window to allow all of these other weird behaviors, and I'll spend much of my time talking about what these weird behaviors are, we find that we need alternative reasoning mechanisms that go beyond what we've done to rationalize the way we think about computation and memory in shared memory systems or single processor systems. Right. So what's the fundamental problem? So in fact, I claim there are two problems. The first problem is this notion of coherence. So when we say coherence, we mean, does there exist an ordering that we can ascribe to the collection of data that I write out? So for example, if I write x to be 1 and then I write x to be 2, will everybody in the world that reads x, will they see either 1 or 2? Or do we allow some people to see 2 and other people to see 1? Now, when we have multi-core systems, shared memory multi-core systems, the answer is every process, every core will either see 1 or 2. We don't know which one, but they'll see one or the other as the last value. And that's because there's a piece of hardware called a cache controller or a bus that regulates all the writes that go out to memory, and it guarantees that you won't allow cores to see different values. When I write a value of x, I'll invalidate all the copies of x that happen to exist in caches on other cores. And so we can make some rationalization over the values that processes can see. But in these kinds of large-scale distributed systems, there is no coherence. That means that if I write x here with the value 1, somebody else can write x there with the value 2, and a third party, which is trying to read, can read 2 or 1, and another party can read 1 or 2, and there's no constraints. Okay, so this is a problem. So what do we mean? What is the semantics of a distributed program that allows this kind of behavior? So that's one issue. The second issue is that there are multiple chefs, multiple cooks that are trying to get involved here, trying to figure out what's going on. So here's a quote from David Hansen, who was the designer of Ruby on Rails, right? And I found this quote to be very telling. So basically, he's a database guy, and he doesn't trust storage systems. I'm sorry, he's a web designer. He doesn't trust the database and the storage systems that the database manages. So what's his claim? His claim is, I don't want the database to deal with data. I'm going to deal with data. And if you want to use Ruby on Rails, if you want to use Rails, then you need to adhere to this philosophy that all of the management of data, all of the synchronization that you do, everything has to be done within the Rails framework. You can't make any you can't make anything but the most primitive assumptions about what the database is actually doing. Now, this might appear to be somewhat draconian, but it seems like a philosophy that should work, except that when people actually try to see whether this avoided errors in code, in the code that they were writing in web code, they found that, well, 15% of the time or so, for the benchmarks that people looked at, things actually broke. And why is this the case? So if I have control over everything, and I don't rely on anybody else to do the heavy lifting for me, how are things breaking? And the problem is that the world is complicated. And so the assumptions that I, as say, a web developer, as somebody who's writing a framework for a web system, may be completely inconsistent with what the database actually is doing. For example, I might assume that the database is giving me serializable transactions. It's actually, when I write a transaction in Ruby, I'm expecting that the database will actually implement that transaction. But in fact, the world is not like that. And many databases, in fact, don't implement serializable transactions. So if I made an assumption that was inconsistent with what an implementation was actually doing, well, you can imagine that bad things happen. And indeed, that's what happens. So now we are in this very awkward situation. We've claimed that we have full control over the world, but in fact, we don't. This is just it's a fiction. We don't have full control over the world because the world is too complicated for us to have control over it. And so we must delegate some responsibility to somebody else. But the minute that we delegate responsibility to somebody else, we're dependent on the things that they do, and that may be completely inconsistent with what we want. And now we're left in this very strange conundrum where we have presumed power, presumed control, but when in fact we don't, and there's nothing we can do about it. Anyway, so the lack of coherence, which makes this problem hard to begin with, and the fact that there's lots and lots of layers in a typical application, a realistic real-world application that involves data, makes for complications. And you see news stories that sort of talk about it. So here's a humorous one where somebody figured out that there were timing issues in the way Starbucks implements its cloud services, where they could essentially continually replenish their gift cards online to get an arbitrary amount of Starbucks coffee. Why you'd want to do that, it's not clear, but you could, right? The algorithm is online. Right. More interestingly, there have been a number of well-publicized exploits of Bitcoin. Right? Bitcoin is the archetypical distributed distributed system with no centralized control. Right? It is the poster child for what modern-day distributed system services ought to look like. And so, not surprisingly, there are numerous cases where people have been able to exploit vulnerabilities, consistency vulnerabilities in Bitcoin implementations to actually steal money from the exchange, which is something that was apparently not possible to do. And so, even though it's theoretically not allowed, right? The fact is that implementations can do things that deviate from the theory. And in one particular case, 12% of a particular exchange was hijacked, right? And that money irreparably lost. Those coins irreparably lost. So our goal is to try to see how we can define systems that have provably correct guarantees, where we can express and specify the kinds of behaviors that we want, and still rationalize these concerns with respect to coherence and multiple layers of abstraction. As others have said, feel free to interrupt me at any time with questions. Right. Okay. So, what do we mean by coherence? Coherence is a property that dictates how writes to memory, some memory abstraction, are ordered. Right. So, something that's strongly coherent means that all processes will view the writes to memory as occurring in some consistent global order. Right. Things which are weakly coherent means that there is no guarantees on how a particular process will witness the writes that are taking place to memory. When we have a distributed system, we have things which are weakly coherent by definition. Okay, so that's one term. The second term that we'll use throughout this series of lectures is consistency. What values can a particular read witness? So I do some writes, and I want to do some reads. After I've done those writes, what am I allowed to read? And what is the relationship between these reads and other reads, between these reads and other writes? And those are the questions that need to be specified in order for us to have any kind of rational understanding of what our application is actually doing. Right? We want to constrain that to the level that makes sense for our application. Now, it's true that we can dictate that we want to behave just like we behave in a sequential setting, without any kind of distribution at all. But that would be a bit silly, right? First of all, why would we want distribution if all we want is the behavior of a sequential system? Maybe there are behaviors that we want that are more general than that. But more importantly, it flies in the face of the need for scale and performance that presumably distributed systems give us, that go beyond what we get out of a sequential framework. So we don't want to simply dismiss notions of consistency that are other than strong consistency. We want to actually consider weaker consistency models as long as they make sense and as long as they're understandable. Right. So, in the framework that we're going to be considering, the picture on the bottom is what is the mental model that you should have. You have a collection of servers. These servers are going to be distributed across, are going to be geo-replicated. They're going to have data that may be local to them, but more likely than not are replicated data that may have been generated somewhere else that sort of flows into them over time. And there's communication between them, but it doesn't have to be a complete graph. Right? Not all nodes need to be connected to all nodes, but what we do expect is that eventually, right, every piece of data that I write will be seen in some form or another on every node that comprises the system. Right. So, what's the ideal case that we want? Well, the ideal case that we might want to think about is one in which every write that I perform is instantaneously witnessed by every node that comprises the system. So, if I were to write the value of v to x, it would be great if there were no cost. If that write were magically found on every node in the system, regardless of where that node was, right? And so we have a global ordering on all writes and reads, and the minute that I perform a write, it's instantaneously available on every node. Right? Similarly, if some other node performs a write with value v prime to x, we expect that write will be visible to every particular node, right? So in this universe, right, there's the sense that all writes are globally ordered in based on the sort of wall clock time that they took place in, right? So if at 2:51 I did a write to x in Seattle, and at 2:51 and 30 seconds I did a write to x to a different value in Sydney, I would expect to see that ordering be visible to all the reads that happen subsequently, right, or in between. Okay. So there's a total order on all writes. We expect writes to be instantaneous in all replicas, and reads always return the last value of the object that was written. So why is this an ideal? Well, it's not too hard to to envision the impracticality of trying to retain this degree of precision on writes. And so one might strive for this, but in reality, it's really, really difficult to achieve. Okay. So here's one way that I could do it. Right? One way that I might achieve it is, well, suppose that I forced all writes to go to a single replica, a single source, right? So I could imagine that there's some node sitting somewhere, and all writes feed into that node. And so when I do a read, I'll always read from that node, right? So I might have this write in Seattle go to some node in Cairo, and that node is responsible for servicing all reads that take place. Okay? And similarly, if at a later time, say 2:51 and 30 seconds, a write emanates from Sydney, well, it might go to the same place and reads that read from that particular replica, and so it looks like we've solved our problem. But I'm sure all of you will agree that we haven't really solved anything. First of all, we've been very loose. This particular model seems to be a bit loose with the notion of what ordering means, right? How do I know that the write from Sydney, the write from Seattle will actually reach Cairo before the write from Sydney, even though the write from Sydney happened later? We don't know anything all about those links that connect these particular replicas. And more importantly, we've sort of defeated the whole point of having replicas and distribution in the first place, because everything now is sort of funneling through to a single server sitting somewhere else. What happens when that server goes down, or there's network traffic, or all the other things that happen in a realistic distributed system? So what we would like is to avoid having a single source of all the data, because that's not what we want. We really do want replicas of data. We want to be able to have multiple places that we can go to get the data that we want. But at the same time, we want to be able to rationalize how the writes are taking place. So here's one way that we might be able to do it. And I don't think that many companies can do it, but Google can certainly do it, right? So what did Google do? Google decided that it, in fact, is very, very important that all of their services see the latest and unique, consistent copy of the data that they're generating, right? So they really did want this notion of strongly consistent data. Everybody should, in fact, witness the same thing. But they were not willing to have just a single replica, a single source for all this data. That wouldn't make much sense given the amount of data that they actually maintain. And it violates their very notion of being able to have availability, of having the data available to them, even if there's network traffic or network problems or server issues. So what Google did was they architected a new system where they essentially had two things going on. How many of you are familiar with Paxos? Right, some of you are. Oh, a number of you. Okay. So do all of you, have you heard of Spanner before? Some of you have. Okay. So this is not a talk on Spanner, but for those of you who haven't, I encourage you to read the paper. It's fascinating. It's a fascinating article about what billions and billions of dollars can do for you. So, so what's Spanner? So Spanner is Google's attempt to be able to have large-scale replication that's fully consistent with all of the data that they're generating. And the way that it works informally is by essentially stratifying their notion of what a transaction and what data means. So in Google's world, there's sort of local transactions. And local doesn't really mean local in the sense of a single server. This transaction is a data center. And the data center could have lots and lots of hundreds of nodes, hundreds of processors. These processors, in fact, could be spread out in various ways. But in sort of the scale that Google is thinking, that's still something that's local, that they can sort of control within the context of some, within the context of the architecture they're building. And so what they do is, for whenever they want to do updates, whenever they want to perform a transaction, they essentially run a Paxos state machine on this particular on the data that comprises this sort of local thing, and they run two-phase commit. They use Paxos for maintaining locks and doing the usual things that you do with a leader election algorithm, and then they run two-phase commit on the transaction. Every once in a while, this transaction may in fact be much bigger than what they can have in just a single data center. It may in fact have multiple data centers be involved, and even there, for that single transaction, they will use a hierarchical notion of Paxos, where there's multiple Paxos replica state machines running on each data center, and then these Paxos local leaders will elect a global leader who's responsible for dealing with all of these transactions, which is responsible for making sure that everybody gets to see what everybody is supposed to see. Okay, so far, a lot of engineering, but nothing particularly revolutionary. But then the third point that they wanted to make was, well, okay, I might be able to deal with a single transaction, no matter how big it is, using a combination of Paxos and all sorts of other services that sit underneath. But how do I know that if I have two transactions running, and one transaction starts after the commit of another, and by after, I mean in sort of real wall clock time, right? This transaction commits at 2:51. This transaction starts at 2:51 and 10 seconds. I want to make sure that the effect of this transaction is visible after the effects of this transaction. I don't want things to get inverted by mistake. Now, Paxos and all this other stuff that they've done, it only deals with this particular transaction here and this other transaction here. It doesn't say anything at all about how you relate multiple transactions together. So Google introduced a new abstraction called true time, which is essentially the realization of the ideal that I talked about in the previous slide. So true time is essentially an abstraction that uses satellites and GPS to come up with a unique timestamp, a global, in like Earth scale global timestamp. And so basically, they have a timestamp associated with every transaction across the entire planet, and that's computed by a collection of satellites, GPS signals, and they will use this particular true time timestamp to determine the order in which these transactions are to apply. Now, I'm simplifying quite a bit here because there is no notion of precise accuracy here. There could be clock skew, there could be drift, and other kinds of things that make this a little bit harder. And so basically, this notion of true time is an interval. And they will essentially stall transactions one transaction from running before another one, even after another has completed, if they can't prove that the interval of the transaction that completed did not finish before the interval of the transaction that's about to start. So, sorry, you had a question? Yeah, so I think it's on the order of a millisecond or so. I forget the exact numbers. So they play around, and it's an engineering question about how they can get the fidelity of the GPS signal and the clock skew to make sure that they don't have this overlap. Yeah. Yeah, so they have atomic clocks too. So I think they have a whole bunch of things that they throw in there. And so I believe that they use GPS as a low-cost thing. Then they have atomic clocks that use to calibrate against the GPS signal, because these replicas can occur anywhere. They can be widely distributed. And so, yeah, there's a bunch of things that they throw into the problem to engineer this. Yes? 10 milliseconds, yeah. Okay. Think about a consensus algorithm. So first of all, we know there's an impossibility result on consensus in the presence of arbitrary failure, right? So Lynch-Patterson will sort of get in the way in preventing you from doing full consensus when you have arbitrary processes that could fail, right? So as long as I allow more than one process to go down that's participating in the consensus, we have no guarantees. So, right, so there's sort of theoretical problems here with looking at other alternatives. But even having done this, right, it is notable, it's a notable fact that nobody else has replicated this particular architecture, right? So Google uses it, but nobody else can, right? Because the underlying infrastructure that's necessary in order to be able to build this kind of system is really, really complicated. And that's one thing. The other thing is, maybe it's overkill, right? For lots and lots of things, maybe I don't really care, right? Maybe it's okay if these transactions get inverted because at the end of the day, it doesn't matter, right? If this transaction is sort of looking at my balance in my bank account and this transaction is sort of looking at my balance in my bank account, what does it matter if I invert them? Or, you know, this guy might be doing a deposit, this guy might be giving me a balance. So every now and then, I won't see the deposit at the time that I check my balance. But at the end of the day, I'll still be okay. So there are lots and lots of instances where the degree of precision that we want doesn't demand the degree of fidelity that something like Spanner gives us. But it's a remarkable existence proof that one can actually build systems at global scale that have strong guarantees on the consistency of the data that's read. Okay. So the question that we want to ask is, are there alternatives that mere mortals can do, right? That doesn't require the level of engineering that Spanner demands. So one alternative, right, that's a bit weaker than the strict consistency that Spanner dictates, is one in which we say, well, maybe we can still have a global ordering of writes, but we'll allow different nodes that are witnessing these writes to witness them in sort of locally consistent ways, but not globally consistent ways. This is sometimes referred to as sequential consistency. That is, I'll allow the writes to take place, and there's going to be some order, and I'll allow different processes to sort of interleave their reads in between these writes, right? And each process will sort of read things in the order in which its computation demands, but different processes can sort of get involved in different ways. So let me show you a little cartoon that explains how this might work. So I might do a write of v prime to x over on the right, and I might choose to copy that, to propagate that write to some other replica. That replica has computations running on it, and it might read, once as a consequence of that write being propagated, it might read that value, right? That's very reasonable. There could be another computation running, or another replica running, so a similar computation, that writes another value, in this case v, and it propagates its data to some other nodes, right? That's also okay, which also sees its value. Now observe that those two reads read different values. It's not like there's instantaneous propagation of the writes, but they're reading values that correspond to something rational. Somebody wrote v to x, so when I read x, I expect to see v, and that's what happens there. So now that same write of v to x on the left, it might find its way to the replica in the middle, right? So now subsequent reads will read this new value. Okay. I write another value, right? And again, I read another value, the same value in some other replica. So the question we might want to ask is, can I now read a value of v prime, right? So we have all these reads that are going on that are taking place in these different nodes. Am I allowed to read v prime having read v double prime, right? And in a sequentially consistent world, right, the answer is no, right? This would not be allowed. And the reason why it would not be allowed is because in order for me to have read v prime, I must have had a write to v prime, right? And that write to v prime is either coming from the rightmost replica or from the middle replica. Both of them have a value of v prime. Both of them have seen a write to x of v prime, right? Well, in some sense, the write to v prime from the right replica hasn't happened, so I don't know about it, so I can't see that. I might argue, or you might argue, but wait a minute, there was a write of v double prime to y that came from that replica, and so that replica right? When it started sending its other data, maybe it could also have sent the write of x to v prime as well. Maybe it sort of propagates that along when it's sending its information. But in order for it to do that, it would have to overwrite the subsequent write of x to v, right? So observe that there are two writes in red, and the write of v prime occurs before the write of v. And so if we were to just say, well, okay, let me send all the writes over, we would find ourselves, and we allowed v prime to be read, we would find ourselves violating sort of sequential reasoning, sequential behavior that we would not be able to have seen if we had just linearized or ordered all of the writes in a line. So this particular notion is somewhat weaker than strict consistency, and it corresponds to our intuition about how processes work in a multi-threaded system, right? Each process operates independently, but we expect to see some kind of sequential behavior that's akin to some sort of sequential behavior, right? Of each individual process on their own. Does that sort of make sense? I will take that as a yes. Right, okay. We could do something a little bit, that's still expensive, right? We're sort of imposing fairly strong constraints on what we can and can't read. We might choose to weaken this notion a little bit. In this particular model, I might say that the only requirement that I'm going to make is that if I try to do a read, right, and I claim that I'm going to do a read of some value, of some variable, I want to make sure that I get to witness the write that happened to that variable in the node that's performing the computation. So for example, if I write x to v, sorry, I write v to x, I expect to read v if I look at x, if I dereference x, right? If I write v prime to x and I propagate v prime, I expect to see v prime. If I send the computation that corresponded, or the value that corresponded to the read of x to some other node. So for example, let's say that I've written $100 to my bank account, and the read is the current balance, right? If I send the current balance, 100, to some other node in South America, I want to make sure that that node also sees the fact that there was a deposit of $100, right? If it didn't, it would look very odd, right? It would appear to the particular person sitting in South America that there was $100 that manifested in his account, and there was no deposit that sort of justified why that $100 should exist, right? It would be similar, for example, to witnessing a tweet without knowing or witnessing a comment without knowing all of the other comments that preceded that particular comment within a particular chain. So this notion of causal dependence, right, obligates me to constrain when I'm allowed to see a read, say in South America, based on whether the previous write that read depended on, or where it came from, was available, right? So we can continue to propagate things in this way, right? We can continue to propagate reads and writes in arbitrary ways as long as we preserve the causal relationship between every write and every read in a particular computation, right? So for example, if that read that was copied from the left into South America that finds its way into Australia at some point, I want to make sure that that read doesn't happen until that write that it depended on also finds its way there, right? So this notion of causality is quite central to our reasoning about what we mean when we think about consistency, right? Consistency, the choice of what values we read, should be based in some sense, in some very deep sense, on causal relationships. What did this particular read depend on? And let's make sure that all of the things that it depended on are also available to us when we do that read, so that we have some kind of we have a rationalization for why things are happening the way they do. Observe that this is not that easy to implement, right? If I'm obligated to have that right be available to me before I do that read, what happens if, for example, I propagate that read over to South America from North America, and the network drops? There's a partition in the network. And this write that needs to go in, that deposit that tells them, that justifies why I'm allowed to read 100, that deposit never actually reaches that particular node, right? What do I do? Well, I'm stuck. I can't do anything, right? Because our rule is that we have to have a causal justification for why certain things are happening. And if that causal justification is not available, then the system would simply have to block and say, we can't proceed. We don't know why this read should be valid. You haven't given me any evidence to indicate that this read makes sense. So causal reasoning, while an effective rationalization for understanding distributed behavior, is a rationalization that's expensive and is not robust in the presence of failure, of network failure, right? Which happens in distributed systems. Right. Okay, so what are we left with? So we want to be able to reason about behaviors of reads and writes and replicas in sort of ways, but we also want to be effective. We also want the system to do something meaningful, even when there's arbitrary partitions, arbitrary network failures in the aggregate. So to overcome this, to sort of rationalize this tension, to sort of try to come up with some way to make progress, we can do something else, which is to say anything goes, right? What does that mean? Well, we can say here's a client that's issuing a series of requests to a database, which is now distributed over the planet. It might choose to write X to some particular replica, right? No problem. It might choose to write Y, and when it writes Y, maybe that write ends up going to another replica because this particular communication channel may be heavily used, maybe there's a network partition. Now the question is, suppose that I want to read X here. I want to read the state of the world, the state of the variable X. What should I do? Well, if I was insistent on causal reasoning, I would say, well, you better make sure that if you're going to read X, that you go to a replica that actually has the write of X that was issued before. So you can provide some evidence that the value that you're reading is not just made up, that it actually came from some particular source that you can justify. But that wouldn't work very well, right? As we said, for all the reasons we said on the previous slide. In particular, if that particular replica is no longer available, it's not accessible, we'd be stuck. So instead, we can say, no, I'll just go anywhere I can, and maybe there's some replica in Australia that's willing to accept my request. That replica has no idea that I wrote V to X, so I'm perfectly fine to read any arbitrary value I want. Now this seems goofy. This seems completely idiotic. Yet, this is the way that distributed systems today are implemented. Right? The vast majority of distributed systems today are based around this notion that you are allowed to read arbitrary values without the need for consistency among the replicas on the values that were written, with this one caveat that says, we know that at some point in the future, right, that write of X to V, or that write of V to X, will eventually find its way into this replica over there, and to all the replicas. And so if you wait long enough, you will see a justification. It may be a time span that exceeds the length of the universe. We're not making any guarantees at all on when that will happen, but we will say that if everything quiesces and the world stops, no more reads or writes take place, and we just allow all the writes that existed before to propagate to all the replicas, we will get the justification that we were looking for. Now that seems like an extraordinarily weak guarantee, right? But it has this one overwhelming advantage, which is that it does not require any coordination between clients and the database, the underlying data store, in order to work, right? And this is why when you log on, as many of you I'm sure have experienced, when you go to Amazon, you find multiple entries in your shopping cart, even though you only ordered one thing. I found on many occasions I've gotten two things. I found occasions where I've ordered something, and then by the time I come back, the thing is no longer in my shopping cart. I've ordered things where there's 100 items, and then all of a sudden, all those items that were in stock disappear. All of these particular anomalies that we see, updates that don't happen, updates that happen multiple times, all these strange behaviors that we see when we interact at a global scale, when we interact with services that operate at a global scale, they're all due to this trade-off, this conscious trade-off that designers have made between the need for consistency, rational behavior of data, of why data exists in the form that it does, and availability. The need to get a response, any response, is better than no response, right? So Amazon would be out of business if you had to wait 10 minutes or 15 minutes before you could get your order completed. And so their rationale was, we'll take a chance that every now and then you'll be pissed off that you didn't get what you wanted, or that you got the wrong thing, or that there was some weird behavior. Because 90% of the time, 99% of the time, things work out the way that you expect, right? It's not the case that networks fail all the time. So when it does happen, we can have our community or our client base be willing to live with that. That's the trade-off, right? Now, that might make good business sense, and I'm not going to argue against that. But the question that we want to ask is, how do we construct a model? How do we formalize? How do we sort of precisely think about these kinds of questions in a way that can allow us to design better languages, better implementations in the future, right? Even if we accept it, we don't have to accept it on blind faith. We can at least sort of try to rationalize it in some formal way where we can explain it in a way that isn't as hand-wavy as I've just done. Okay. So the weakest guarantee that we have in distributed systems is this notion of eventual consistency that says that as long as we allow an arbitrary amount of time, we can justify the value of everything that was written based on previous rights, right? That is, every replica will eventually come to some consistent state, some state that we can explain, right? That doesn't, where we don't have things that just seem to manifest from thin air, right? But there's a whole bunch of questions that open up once we admit this kind of behavior. And here are just a few, and I ran out of space on the slide, so I stopped. But there are lots more, right? So what values do replicas, what values can replicas see? Can we actually make up arbitrary things from thin air based on this? When do they see them? What is the notion of time? We have, in computer science, we have a very, very awkward dialogue when it comes to notions of time, right? We think in terms of logical time, but then there's a physical clock sitting somewhere here as well. How do we sort of rationalize this? What happens if I send multiple requests or different requests to different replicas, multiple requests to the same replicas? Do I have any guarantees on the order in which these requests are satisfied? Eventual consistency requires that the system quiesce, that eventually updates stop. But in practice, right, updates may never stop, right? I might be running transactions that are consuming things all the time. Amazon runs 24/7. It never stops. It doesn't say, sorry, we're offline for the next 2 hours while we wait for everything to quiesce, right? That would be bad. So updates don't stop in practice. So we have to do something about that. Databases have strong guarantees on the behavior that they wish to enforce, right? So those of you who are familiar with the ACID properties in database know that the I in ACID stands for isolation. We want to make sure that certain values aren't seen, that a database runs in isolation from other updates. How do I reason about consistency and isolation? They seem to be related. They both have to do with when values are seen. How do I know what those how do I rationalize that? What happens if I've got two replicas that write different values to the same location, and they both land up at the same point? What do I do with that? How do I figure out which one should win, which one shouldn't? What do we do when I do want stronger consistency? If I'm running in a world where I've got the weakest guarantees, how do I sort of inform the system that I want something better than what you're giving me? Am I obligated to sort of have the client be responsible for doing the synchronization and doing all the heavy lifting to get that done? Or is there things that a runtime system or a compiler or a program analysis or any other tools that sit below the client, are there things that those tools can do to overcome or to provide these stronger guarantees? What about transactions, right? So far, all of the cartoons that I've drawn had to do with a single object, a single variable, x or y. What happens if I need to think about x and y together? And yet these things, these operations on x and y, even though they need to be viewed semantically as an aggregate, they might end up in different places in ways that I have no control over. What about other kinds of application level constraints? Right? So in databases, for example, there's something known as an integrity constraint. If I've got two tables, right, one with users and one with, say, the posts that they've made, Facebook posts they've made or Twitter comments that they've made, if I delete the user, I'd really like to delete these comments as well. Well, they're not in the same place. They're different things. They have different, they reside in different pieces of memory, but I need to somehow relate them together. Now, looking at memory, I have no clue what those relationships are. That particular property, that there is a constraint between the users and the posts that they've made, is something that only the database, that the application developer knows about. So how does an application developer convey to the storage system that there are properties, relations between the data that exists there that aren't manifest within the system itself? So all of these questions require answers. So it's a rich space. You have lifetime employment in this world, right? Because there's no clear way to sort of address them. Okay, so much of what underlies what we're going to talk about was sort of formalized by Brewer in 2002, and it's this very famous conjecture called CAP. Right? And it was a conjecture when Brewer started it, and Gilbert and Lynch a few years later actually proved it, so it became a theorem. Right? So what does CAP say? So the observation is very, very simple, but has significant implications for systems design. So there's sort of three notions that we've sort of introduced informally so far. The first is this notion of consistency. What values can I read, right, based on the values that have been written? The second is availability. How fast can I get a response to a particular query that I make? So if I want to read the value of x, how long do I have to wait to get that value back? And partitionability. I'm living in a network, I'm living in a distributed system, and I know that things are going to fail. So what do I do when things fail? Now, in practice, since I've got a distributed system, I must accept partitionability. That's the fact of life. The network will fail. There will be hiccups in the way that I communicate with other nodes. So let's assume that I have any system that I design must be robust in the face of network partitions. It simply cannot say, oops, the network is down, sorry, come back later, right? That would be bad. So we need to make sure that we have a design that is robust in the face of partitionability. So what the CAP theorem basically says is, if you give me partitionability, you will only be able to achieve one of consistency or availability. That is to say, if you want to be robust in the face of partitions, you will either get consistency, that is, you can make sure that all the data that you see, everybody sees the same data, but if there's another failure somewhere, if a node goes down or something, you're not going to get a response. Or you can get a response no matter what happens, right? No matter how badly the network breaks or how many replicas fail, but you're going to give up consistency, right? You can't have it all, right? You can have your cake, or you can just look at it. Or you can go hungry, but at least you're still walking, you're not waiting, right? So these two points in the spectrum inform the way we design systems today, these distributed systems today. So Spanner, right, and databases like MongoDB are examples of systems where they're strongly consistent, right? But in fact, they will lose availability. If my leader, in my Paxos leader election algorithm, if that leader goes down, I'm going to wait for it to come back up. I'm not losing data. It's not like I'm going to get wrong data. But if, there's a radiation blast and all of Google's servers, on one side of the universe, on one side of the planet, fail, I'll wait, right, until they come back up, right? So that's one world, but you get consistency. When you do get, when everything does come back up, the data that you read is, in fact, the data that you wrote, right? You're not going to see anything weird. The more interesting, the sort of fun side of town, right, is what we'll talk about in the remaining part of in the time that we've got, which is data stores in which we will sacrifice consistency. We'll say, we're not going to worry necessarily about what we actually read based on what we wrote, but we will ensure that we'll give you back something, right? You'll get back something. It may not be what you want, but you'll get it back. And so you can keep doing something with what you've gotten. Yes?
So I was under the impression that there's sort of like probabilistic story for spanning, though, that they can guarantee that with some bound, the service is sufficiently available. Right? Do you know if it's
Yeah. So Spanner provides high availability up to some particular bound based on the the likelihood that that a quorum will fail, that you will not be successful in getting a right quorum, right? So in practice, right? So this is Google's line, right? In practice, it's okay, right? You don't lose half.
Basically have cap.
Yeah. Well, no, I'm not willing to. Well, basically in big quotes, right? So if I were my system, and this is where the tension between a systems designer and a PL person comes into play, right? What does it mean to be 99% sound? Is that good enough? Okay. And people might argue that soundness is overrated, but it's what pays, gives my paycheck. So I'll go with the idea that no, you really do want soundness. You really do want to be able to have some guarantees that are, in fact, provable. And so you're right. Google works most of the time, right? But in fact, the ideal of being able to get strict consistency and availability, it's not there. Yeah, there's a bounded probabilistic story. It's a wonderful story, right? I'm glad they did it, right? We're not going to do it, right? So what do we do? And what do the peons below that, what do we end up having to do? And the story today is that people, in fact, sacrifice consistency, right? They're willing to sacrifice consistency. There's lots of major services that run Cassandra or Dynamo, right, or React, and they don't have the kind of consistency that Google offers by default. So the question really is, in my mind, a language design question. You can get by most of the time without having to pay for consistency, right? Google pays for consistency even if they don't need it, right? They're willing to pay for it because they say, okay, we're going to do it once, and all of our servers are going to use it, and they can amortize the cost based on all the other things that they offer. But if I don't have the pockets, if I don't have Google's pockets, I have to make a much harder choice. And for me, the choice is, if I don't need to pay for it, I shouldn't pay for it. I want to go the other way. Most of the time, if it is the case that most of the time, I can live with the weaker consistency model because I do believe that there won't be partitions, and I can get consistency and availability because there is no partitions, then only in the cases where I absolutely need consistency, say, when there is a failure, that's where I want to invest my design work. That's where I want to sort of put in the resources to get things right. But maybe that's a very small fraction of the common case. So if the common case is we can live with inconsistency, maybe that's okay. So we'll see examples of that. Are there other questions about that? Okay. Right. Okay. So here's the idea then. The idea is we're going to work within the context of a model that's extremely weak, that's eventually consistent, and then we're going to try to, and we'll get availability for free, and then we're going to try to strengthen the consistency model on demand when we need it. So there are a couple of things that we're going to have to do then. We're going to have to figure out a way of expressing to the system when we need it, and then we're going to have to figure out a solution. having expressed our need, for the system to actually provide it, right? So these are the two things that will end up forming the bulk of what we want to talk about. Right. So, yeah. So we're going to be living in this world of Cassandra and React and these other kinds of systems where we're going to assume that we're always on, but we're going to allow weak consistency. And the reason is we're assuming that there are failures that can happen, right? There will be partitions that can happen, and we can't control when those partitions will take place. So there's this question that I've alluded to a number of times on this difference between what we mean by correctness and what we mean by performance, right? Because after all, that's the game that we're playing. If I only cared about correctness, then all of this becomes moot, right? I will have to pay the bucks to do what Spanner does or something like that and make sure that everything is consistent. If all I cared about was performance and I didn't care about correctness, then I'm equally in good shape in terms of having to spend brain cycles. I'll just do eventually consistent. I'll just send data wherever it goes, and I don't care. I'll get, things will work fast, but it won't be necessarily correct. So these are the two ends of the spectrum. But the interesting thing is that much of the world and much of what our desires are, like most things in life, are in this gray area where it would be nice to get correctness, but I really don't want to give up performance. Or conversely, it would be nice to get performance. I really don't want to give up correctness. Can you do something for me, right? And this becomes a negotiation. So here's examples. If I'm doing, say, bank deposits, right? I may be willing to say, look, I really want to get out of the ATM. I don't want to stand waiting for the bank to tell me that the deposit took place. I'll believe the bank, right? We have some trust that the bank is going to do the right thing. It may take a day for that deposit to show up. I'm willing to live with that, right? That's the notion of a weak consistency guarantee that a client is willing to accept. If I'm looking at flight pricing on a travel website, it's true that prices can change underneath me, but I'm willing to believe that most of the time it's not going to happen. And even if it does happen, it's not going to happen so dramatically that it's going to affect me, right? There's an understanding, an implicit contract between a flight website like Expedia or Kayak and me that says between the time that I look at a price and the time that I actually click the purchase button, maybe the things have changed. But I'm willing to live with that, right? These are examples where it's not necessary for us to architect a system that provides full consistency. On the other hand, things like stock quotes, stock trading, right? If I claim that I want to purchase a stock at $1, it's not good enough if the stock changes underneath me to $2. That would be bad, right? So there's expectation that between the time that I press the purchase button and the time that the order goes through, that in fact the order has gone through at what I expected. Issues with security, distributed security, configuration access. If I change my password, I expect that all replicas will see my password, will see this new password at the time that I press the change password button, right? It would be bad if there was a security vulnerability and it took a day or 2 days or whatever for that to be repaired as updates meander through the system. On the other hand, right, there's a whole bunch of applications where we regularly live with various degrees of weakness, various degrees of inconsistency. I lose email all the time, and it's not just because I delete it, right? It just doesn't show up, or it shows up later than I expected. It's okay. I know, I'll complain, but I'll live with it. Calendars, distributed calendars sometimes take time to propagate to everybody. That's okay. Social networks are a really good example, right, of cases where a particular post may take a while to show up, but we don't sort of make such a hue and cry over it. What we do expect, though, is that there's some rationalization that I would rather see. It may take a while for my post to show up, but I don't want a later post that I wrote to show up before an earlier one. That would be stupid, right? So there are some constraints, but we can weaken the degree of consistency that we want, and so forth and so on. So the real question for us is, how do we manipulate this gray area, right? Because there's lots and lots of examples of that. And can we sort of design tools, design abstractions that lets us express these weak and strong constraints reasonably efficiently, reasonably cleanly. Right. So what I'll do for the remainder of this class, and then we'll sort of continue next time, is give you a model, give you a system model of how we think the world works, right? And we'll sort of build on this model in coming up with new abstractions that can leverage over, that we can use to sort of program against this model. So here's our model. Our model is we have a collection of replicas, and these replicas are going to contain data, right? X, Y, and so forth and so on. But they're not going to contain values. They're not going to contain the value 13 for X. Instead, what they're going to contain are things called effects. So they're going to contain the operation write 13 or write 7 and then add 6 to the thing that you previously wrote. Things like that, right? So in this particular picture, X is bound to things that say write an effect of write x1, another effect of write x2, and those metavariables, write x1, write x2, represent some operation that has to take place. Okay? So I have replicas that have effects and variables, right? And I have something called a session. Think of a session as a client, as what a client does, right? So a client might make a call to foo, to a method foo associated with this object x, right? And the effect of invoking foo on object x might be this write of a new value, right? Foo might end up writing a new value into x. Now, I have a collection of replicas, each of which have effects, and I have sessions, which consists of a collection of operations, but I'm making no constraint that a particular operation that a session issues has to go to the same replica that other operations that session issued went to before. So in this particular picture, the call to foo and the operation on foo is taking place with respect to the data stored in the replica on the left. Another operation on x, this time bar, is going to another replica, right? Which has not seen write x1, write x2, and so forth and so on, right? So the model is very general. We have sessions, which are a series of operations. Sessions these operations get executed on replicas. Replicas store these operations, and every now and then they will execute these operations. They'll run these operations to produce something which is meaningful to the user, and then they'll return that. And in the background, these operations are going to get propagated from replica to replica in ways that we have no control over. We, the application developer, has no control over. So for example, the replica on the right will propagate the fact that it's seeing an operation of write x3, and it'll propagate that information to the middle replica. But when it does it, how it does it, we don't know. Okay? Right. So an object is a set of effects, reads and writes and things like that. A client consists of a session of a collection of operations. And in the background, replicas are going to communicate with each other. And clients are free to communicate with any replica that they want for any session. This is a very, very general model. Right? So here's an example. So I have two clients, Alice and Bob, and I have a replicated store, right? And Alice and Bob both sort of store their particular effects. Let's assume that they're objects, right? They're both clients and objects, right? And so in replica 1, Alice's effects was a deposit of $10 and a withdrawal of $2 from her bank account. And replica 1 also has witnessed the fact that Bob has deposited $9 into his account, and so forth and so on, right? So Bob, in one session, decides to deposit $5, right? When he chooses to do that, and then he's going to withdraw $6. So there's sort of two operations here, each of which have effects, one called D5 and another called W6. Okay? So there's a relationship between the deposit and the withdrawal. And that relationship is going to be captured by this relation that we're going to call session order, right? So a session order relation defines the sequence of operations that a particular client is going to execute. Right. So just as we saw on the previous page, the deposit of 5 can go to replica 1, The withdrawal of 6 can go to replica R sub n, right? And once they reach those replicas, we're not going to do anything. We're just going to record them, right? So replica 1 says for Bob that he issued a deposit of 5. Replica n says Bob also withdrew 6, right? Now observe that replica n doesn't know about the deposit of 5, and replica 1 doesn't know about the withdrawal of 6 at this point. Okay. In the background, we're going to sort of communicate data. Now observe that I could also do other kinds of computations on replica 1, right? I might say, Bob might issue a request that says, what's the value of my bank account at this point, right? And if that particular request went to replica 1, the response would be 8, right? Ignoring the fact that there was also a withdrawal of 6 that he issued before. This is perfectly acceptable, right? So eventually, everybody will get to see everything else, right? That's the hope. That eventually, everybody gets to see all of the data that they wrote. Okay. So as I mentioned before, there's this get balance operation that I might issue periodically, right? But that Bob might say, having deposited 5 and withdrawn 6, you might say, what's my current balance? But that get balance operation, if it's executed after replica n has transmitted the withdrawal of 6 to replica 1, we get to see all of the operations that have been issued thus far, right? And we're going to express the notion that a particular operation sees another operation as a relation that we will call viz, for visibility, right? So we say that the get balance operation witnesses or has visible to it the effect d3, d5, w6, okay? And so we get to write that as well, okay? So our system model is comprised of replicas and sessions and these two important relations. Session order, that says the order in which a client issues requests, and visibility, the observation of previously issued effects based on a given replica, that are available on a given replica. Does that make sense? Okay. Nice. Right. Oh, sorry. Yeah.
So we know that session order doesn't imply visibility.
Yes.
But is the opposite true?
No. Right? The fact that I saw that GB saw W6 was purely serendipitous, right? It just so happened that the W6 effect was propagated from replica n to replica 1 before the get balance of operation was issued on replica 1. But it's quite possible, it's quite conceivable, that this get balance operation could have been generated on replica 1 before that W6 effect was propagated, in which case the get balance will only see D3 and D5, even though the withdrawal of 6 is in session order with respect to it.
I think that's the opposite of what you said.
Oh, sorry.
If it is the case that get balance, that we have a get balance, let's say, if W6 is related to get balance with the visibility relation, does that imply that W6
No. No, because there could be another session that did the W6, right? Right? So Bob may have clones that are running on different replicas or different sessions. And so, yeah, there's no correspondence. Right. OK. So with this model in place, let's just, I'll conclude by giving you 3 examples of goofy things that can happen, right? So I've come up with a model. You should be very skeptical about the validity of this model after I tell you all the bad things that can happen. And so our goal is going to be to try to overcome these sort of bad things in subsequent designs. So here's an example of things that can happen. I have 2 sessions, right? In session 1, I deposit 100, right? And I withdraw 80, okay? Now, that relation viz and SO that we see hanging off that arrow between deposit and withdraw tells me that when the withdrawal happens, it took place on a replica that also happened to have seen the deposit, right? And the session order is obvious, right? The withdrawal happens after the deposit, so there's an SO relation as well. Now, imagine that I have another session, right? And let's assume there's a single bank account, right? There's just one account. This other session withdraws 70, okay? these arrows, there's a visibility arrow between the withdraw of 70 and the deposit of 100. That means that this session, that this withdrawal of 70 might take place on a replica that happened to have witnessed the deposit of 100. Okay? Importantly, observe that there is no arrow between the withdrawal of 80 and the withdrawal of 70. Right? So there's one replica that sees deposit 100, withdraw 80. There's another replica that sees deposit of 100. And it just so happens that the withdrawal of 70 happens on that replica. Okay? So now I try to do a get balance. Right? I try to do a get balance. And the get balance operation, right? The get balance operation happens on a replica in which all of the actions have shown up. Right? So when this get balance happens, it just so happens that this withdraw of 80 that the withdraw of 70 never saw, right, now shows up on that, now shows up. Okay. So if I want to make sure that I don't overdraft my account, right, this particular model is now going to prevent that. Right? Every replica, when the two withdrawals happened, they both think that there's enough money in the account. Right? The first replica says, oh, there was a deposit of 100, so I can certainly withdraw 80. The second replica says, oh, there was a deposit of 100. I can certainly withdraw 70. It just so happens that the two withdrawals don't know about each other or didn't know about one another when they took place, when they were executed. Eventually, the system realized, propagated all the data that it wanted so that the get balance that ultimately took place found a negative balance. Right? So this is an example of a missing dependency. Clear? Right. Here's another example. I have 3 sessions now, right? A deposit of 100, a withdrawal of 50, and a third session that's trying to do a get balance. So let's assume that there's a visibility operation. There's a visibility relation between the deposit of 100 and the withdrawal of 50. That is, the deposit of 100 took place on a replica. The withdrawal of 50 took place on that same replica, saw the deposit of 100, and said, I'm OK. I can withdraw $50 given that there's been a deposit of 100. The third session happens on a replica where the withdrawal was available, right? That withdrawal of 50 ended up on this replica. It was fine. And then found its way to another replica that the get balance propagates to. What does the get balance do? The get balance sees the 50, hasn't seen the 100 yet, because that deposit hasn't sort of found its way to session 3, or to the replica that session 3's operation is being sent to, so we get a negative balance again. Okay. Even though this should be allowed, right? There is, in fact, enough money in the bank, but we'll get an overdraft. We'll get an error message. So this is a lost update problem. This can also manifest as a consequence of the sort of very weak model that we've propagated. Here's the third example. So I just have one client now that does a deposit and a withdraw, right? So the withdraw and the deposit see each other, right? They happen to go to the same replica. So the deposit of 100 and the withdrawal of 50 happen on the same replica. The withdrawal says everything is OK. But the get balance, unfortunately, doesn't go to that same replica. It goes to another replica that only witnesses the deposit, but not the intervening withdrawal, right? So it's going to tell me a balance, which is, in fact, inconsistent with what reality is. So having done this get balance of 100, I'm now perfectly free to withdraw 100 because I look at my balance and I say, oh, I certainly have 100 here, so let me withdraw it, even though there's been an intervening withdrawal of 50. So the model that we have does not enforce or does not require that all of the operations that take place in a session must be available to all of the replicas that those operations go to. Right? So missing dependencies, lost update, and no session guarantees constitute the sort of large class of errors that can happen, or anomalies that can happen in an eventually consistent system. So what we're going to try to do, and I guess I'll close here, is next time give you an operational semantics. Actually try to formalize this in a concrete way, in a precise way, and then we'll try to come up with a series of techniques that can sort of allow us to program against this kind of model. Any questions? Great, thanks.